What do you know about the Planck length? Most likely, the first thing you'll recall is that nothing can be smaller than this value. And doesn't it seem to you that such reasoning greatly generalizes the question, really abstracts it from reality? Maybe we want to be a bit mischievous and peek a little deeper than what the Planck length shows us. Let's try to figure out what actually happens at scales smaller than the Planck length. If we try to break through to a level smaller than the Planck length, what will we do? That's right, we'll set off on a magnificent, amazing journey, not to the center of the Earth, but to the center of a black hole. Any attempt to measure a quantity that is comparable to or smaller than the Planck length could actually lead to us, well, creating a black hole. Unfortunately, for now, there are no energies available in our conditions that would allow us to carry out such a measurement process. But most likely, all of this has gotten mixed up in your head. How can that be? Why is it like that? Where did these black holes suddenly come from? Maybe it's just some kind of curse of these measurements, or maybe something mystical. No, in fact, everything here follows from physics, or rather from mathematics. Very often, when we talk about things like this, very often when we discuss certain phenomena that are, to some extent, theoretical, the main question arises. If scientists speak so confidently about certain phenomena related to such scales, magnitudes, and concepts, then how exactly do they obtain this information? The scariest part is that all this information comes to us from mathematics. Essentially, all the things that we cannot study, cannot touch, cannot feel, we calculate mathematically. And here, you can criticize this approach and you would even be right on the one hand, but on the other hand, we simply have nothing better. That is precisely why physics usually originates from mathematics. This is especially interesting when we talk about fields related to quantum physics, areas involving some intriguing energies, high energies, and things like that, where we can't do anything directly. Again, you can continue to criticize this, continue to treat it with skepticism. However, most experiments that were once only at the theoretical level, if it's even appropriate to call them experiments, let's call them thought experiments, eventually find their confirmation. For example, the aspects related to the operation of the Large Hadron Collider were initially just calculations on paper, or perhaps in computers. When technology reached such a level, we were able to test this, to put that mathematics into practice, and confirm that, yes, our hypotheses and theories were largely correct. Regarding these facts, well, for example, the most famous discovery is the Higgs boson. Now, you might be wondering, how exactly can we measure the Planck length? In order to measure the Planck length, we actually need to compare it to something else. And to measure something comparable to the Planck length, we also need to somehow run it through this same process. For this, we chose a photon. So it turns out that we can try to measure the Planck length with a photon. And this is exactly where our favorite Gordon Freeman comes in with his cart, pushing it somewhere into the reactor's epicenter, and then an extra dimension opens up, just like in that amazing game, if you remember. Well, basically, now that we've discussed all this, we need to turn to the specifics of these measurements. The paradox here is that if we try to use a photon for this, the photon would need to have such a high energy that the very appearance of such a photon in space would itself produce exactly the interesting effect we're discussing. It is precisely such a photon that would create a black hole. Why? Because energy and mass are connected, and we remember that when one increases, the other inevitably increases as well. Essentially, an object possessing enormous energy in space will cause gravity to become so strong that it will facilitate the formation of that very black hole. The next interesting point that awaits us here is the very behavior of spacetime itself. Essentially, we are now answering the question, what will happen if we try to go beyond the Planck length to find something smaller than the Planck length? The first effect we can expect when trying to measure this is, in fact, the transformation of space into a singularity and the formation of a black hole. And the second effect we have the right to expect is the emergence at this scale of strange and incomprehensible behavior in what we previously called smooth space, and the formation of quantum foam. And so, yes, beyond the space described by the Planck length and Planck units, there will be a quantum soup, my friends. So, after hearing this, what can you say? Alright, if things are so bad with the photon, then let's try using some other quantity. Let's try to somehow measure these quantities in a different way, so that we can avoid the photon having such enormous energy. But that won't work. The problem lies in the very methodology itself, in the physics and logic involved. We will always face the fact that in order to measure something, we need energy, and that energy will be practically infinite at the level we are trying to reach. This is a direct consequence of the physical principle of localization. As we mentioned earlier about the laser rangefinder, what do we essentially need to do? To localize a certain measurement there, to localize it here, at the measurement point, and to measure the difference of what essentially we are using as the measurement factor. It could be a photon, it could be any other particle, but that's not the main point. The point is that the lower the level we need to investigate, the more energy is required for localization. There's no other way for it to work. When the wavelength is huge, our ship can completely climb onto this wave, and essentially, it just won't be able to feel the full effect of the wave. It's a different story when the waves have short wavelengths. And here we can recall, for example, if you've ever been in a boat, it's easy to remember this as well. You sail across the surface of the water, which is no longer smooth if there are waves, and you notice that if the wave is long, it rolls in, lifts the boat, and you hardly feel any interaction at all. But if the waves are small, for example, if someone nearby starts up a motorboat, you notice that you're constantly being tossed around on these waves. And essentially in this way, we can demonstrate that if the wave is long, then the wave does not interact with the macro object. If the wave is short, then the wave does interact with it. This shaking is the interaction itself. It is, in essence, an analog of measurement. Then we end up with a situation where we need waves with certain characteristics. It works in much the same way with measurements. In order to achieve the desired effect, we actually change the characteristics of the radiation we are working with. Similarly, when X-ray crystallography emerged, and thanks to the ability to apply this principle in practice, we were able to study crystallography, which, as you know, I have told you a lot about. When we talk about this interesting effect, there's something else as well. We need to recall a very simple pattern. As I mentioned earlier, essentially all of this comes from mathematics, but the mathematics here is quite solid, and from this comes another interesting principle. All of this is connected by a single equation. This also implies something else, that along with changing the parameters of the radiation we're working with, whether it's a photon beam or an electron beam, or whatever else we're using to probe our sample, we also get an increase in energy. Because in order for the electricity to have the characteristic that we need, for example, with the frequency that can interact with the atomic lattice, we need to increase the energy. An electron beam has more energy than a regular optical lens. Or to put it differently, than a regular optical objective. And the light we use when working with an optical microscope has less energy than the light used in an electron microscope. In an electron microscope, it's essentially not even light anymore. And here, before we go any further, it's worth mentioning another important principle. At one point, we discussed the concept of wave-particle duality. And we also found out that the wave-particle nature is, let's say, the fundamental principle that applies to all particles of a certain size. Moreover, it also applies to larger particles, but in those cases, macroscopic effects, as is commonly believed, suppress the principle of wave-particle duality. Moreover, we have often said that the term wave-particle duality itself is to some extent outdated. And today, it would be more accurate to say that we have a certain wave-like object that sometimes exhibits particle-like properties. This means that any object we work with, any object we try to interact with, any particle is essentially a wave. A wave with certain characteristics, a wave with specific parameters, a wave with some properties that we also encounter in the macroscopic world. I mention this for one simple reason. In order to perform any measurements, we will inevitably have to interact with this wave. Therefore, in any case, we will run into the principle we discussed earlier regarding the diffraction limit. Every new level we try to reach, every smaller scale we attempt to observe, implies that the very nature of physics, the very nature of the phenomena we are dealing with, requires an increase in the energy with which we are essentially trying to look there. Simply put, each new and smaller level will require an increase in energy. This principle, regardless of whether we're talking about optical microscopy, X-ray structural analysis, or anything like that, will run as a continuous thread throughout our entire discussion. At this point, you can even forget what we said about the optical microscope. You can already set this principle aside for now. Another principle is important. To reach a deeper level, you need more energy. Just make a little note for yourself somewhere in the margins that this didn't come out of nowhere, that this principle followed from those simple examples we discussed. Because often, when you start talking about this, people get everything mixed up and don't understand how we connected higher energy, some photons, and then also Planck scale quantities. We connected this in a simple way. We traced it from the moment we worked with the optical microscope, and then we said that all objects are essentially wave-like, and stated that this is a general principle for all of physics. I hope this is an important note that will bring clarity to our discussion. We need to remember that energy is equivalent to mass, so we can say that as we increase the energy required to reach a new level, we will inevitably increase the mass of the object that is trying to reach this new level, that is trying to, let's say, provide us with some information about these measurements. So at some point, by increasing the energy of the object and thereby increasing its mass, we will reach an interesting value. To be honest, I can't pronounce the Schwarzschild radius correctly right now. Oh, it's embarrassing, of course, but for some reason my tongue gets twisted when I try to say it. But the point is something else. As we keep increasing the mass of the object we're working with, we will inevitably reach a value at which space will begin to turn into a singularity, and in this way, we will create a black hole. From the equality of these values, we can talk about a certain Planck length. Essentially, the Planck length is the very length at which a black hole has not yet formed. It is precisely the length at which we can still rely on the principle of localization and the principle of straightforward measurement. Anything smaller is no longer a length. This does not mean that nothing exists there. It does not mean that it is some completely different universe. It means that our physics does not work there. But the most interesting thing is that we can approach this very point, this very principle, from the perspective of Heisenberg's uncertainty principle. What do we need in order to measure the position of a particle as precisely as possible? We need a photon, and in this case, the photon will have an enormous momentum. This photon's momentum will lead us to the same values, but from a different angle. Photons with such energy will, in essence, loop space back on itself. In other words, we would be dealing with a completely incomprehensible substance that cannot be measured. We will try to measure the position of the particle more precisely, increasing the photon's momentum, ramping up its energy, and in doing so, we will end up looping the measurement of what we are trying to measure. And what is this magnificence, this circle? Essentially, it is infinity. And so, approaching from the side of Heisenberg's uncertainty, we have arrived at the very same value at which the Planck length operates. It is often written in articles on this topic that such a size can be considered a kind of fundamental boundary of the universe, a sort of protection of the universe from attempts to measure at a level below this, and a barrier that cannot be overcome. From all this, you should have understood the most important thing, that something smaller than the Planck length can very well exist. There is no such restriction there. But measuring something at the level of the Planck length, or more precisely smaller than the Planck length, would already be, let's say, a big problem. A big problem because it would require enormous energies that arise from the very act of measurement and the comparison of matter with a wave. In order to work with such energies, we would have to modify our existing Hadron Collider and make its circumference just a bit larger than it is now, only by a few thousand times. We would need to build a collider with a circumference of 4,000 light years. Fortunately, such things are not available to us yet. In order to dig down to that level, we actually need to learn how to do that. Whether we should learn or not, ask Dr. Freeman, he'll tell you. Perhaps it's not the best idea, at least with the level of physics we have right now. And we get the same thing from Heisenberg's uncertainty principle, where everything again hits a dead end, everything goes in circles again. So essentially, yes, we are dealing with a kind of, let's call it, barrier, with a certain value that limits the very concept of spacetime.